students, this is Mrs. Marshall, and I am going to be doing the next few set of some videos for us and give Mrs. Holmquist a little bit of a break since she has done most of them, if not all of the ones from Chapter 1. As we begin Chapter 2 together, we're going to actually start in the section 2.3 and have a brief conversation about limit notation and bring back a little bit of that before we actually start the full Chapter 2. So we're going to go 2.3 first and then go back and do 2.1 and 2.2. Those two sections have some limit ideas in them, and it's best if we could just review some of our pre-calculus information and add a little bit of calculus spin to it before we get into a little bit more. Our goal here in this Chapter 2, by the way, is to get us to slowly approach understanding derivatives in a little bit more of an algebraic way. So far, we've worked a lot in Chapter 1 on the graphical ideas, increasing, decreasing, concavity, positives, negatives, inflection points, and most of that had to deal with graphs and what Holmquist and I call the T-chart information. And Chapter 2 begins to get us into a little bit more of the algebraic approach to understanding derivatives. And for us to do that, we need to have some limit concepts. So today in 2.3, okay, we're going to do basically one major component, and we're going to make sure that we really understand the language of limits and the formal ideas behind them. And then tomorrow, in the second half of 2.3, we're going to do a little bit more on what we understand to be continuity. So those are our two main focuses in this 2.3 section. What you see here in the notes in front of you on the screen is recalling sort of the informal way that we talked about limits in pre-calc. And the limit notation that we use in pre-calculus is the same limit notation that gets used here in calculus. We're just going to be a little bit specific about some of the formality of those limits. So right here in the box of information is what you guys saw for limit notation. Just a couple of highlighted reminder things below that. You remember, a limit is really the idea of a function approaching a certain value as the x's approach a different type of value. So x approaching a, this x being approached to a with the arrow part below that, gives us an idea of what the y's might approach. So sometimes we need to remind ourselves that in the circle here is the x concept, and the f of x, also the y's are approaching a certain value here, L. So we did this a few times in pre-calculus with dealing with infinities and negative infinities, and then also we worked in pre-calculus with using those with vertical and horizontal asymptotes. So we're going to also kind of have some of that information, but we're going to bring in a little bit more of some different functions. And we also kind of use this informal idea here is that f of x approaches some L value whenever x approaches some a value. How you say the limit and understand it can be used either one of these two ways. It really is the same concept of the function approaching some x value and what y value does it go to. Right below this here in your notes, here we have one example that we're going to start off with just that basic idea. What is the limit as x approaches 3 of an x squared function? So I'm just going to help out here with just a simple graph first, just to make sure we are clear-cut about what that limit notation meant from pre-calculus. So here's just that nice basic x squared function. And when we have this concept of the limit, here, as x approaches 3, let's just say that here is 3. And the idea behind that is as we approach 3 here or here, okay, that we're slowly getting close to this particular y value. And we kind of want to know, as x approaches 3, what is the y value that it's approaching? That's really the limit question. So in this case, we're very straightforward because we end up going in the y direction toward that same value of 9. Because that 3, that x squared function, gives us a y value of 9. So this limit is just simply answered very nicely with the concept of equals 9, okay, and that limit approach from both sides going towards that 9 value. All right, so that easily identifies something with a nice simple function, but of course we're not always going to be that simple. In fact, now we start to get a little bit more fun. Okay, what is the limit as x approaches 3 again of x squared minus 9 over x minus 3? Okay, so when we look at this particular function, number one, okay, we don't necessarily have an exact graph off the top of our head in mind here, but we can make a graph of that. But really, if you think about this, and I'm sorry because I'm going to tap backward just a little bit, I mean, in our last example, we could have found this answer of 9 without really a graph. The graph was awesome, and it gave us a visual picture, but really, we could do this particular limit part by just plugging in 3 to the function, and it would have given us that same answer. And because we know what x squared is, we certainly know that the limit would approach that. But when we have this function, and we think about it in the same way, what happens when we plug in 3 for x? Well, when we do that, we get 9 minus 9 on the top, and we get 3 minus 3 in the bottom. And we are certainly intelligent enough to know that 3 isn't even a possible number, because that gives us a division of 0. So plugging the function in doesn't really help us out. We can then grab our graphing calculators, and at this point, we could look at the graph of this, okay, and understand that particular concept. So we're going to look at this in 2 different ways. So I want you to grab your graphing calculators, okay, and if you've got one handy, I want to see what the graph of this looks like. So I want you to bring up that function x squared minus 9 over x minus 3. And although you have your graphing calculator with you, I'm just going to make a sketch of that and not bring up the graphing calculator on the screen. So if we look at that graph just very briefly here, okay, on your graphing calculator part, okay, what you should be seeing, okay, on your calculator screen is a very linear idea. And it should look something like this. Okay, and we are intersecting on 3 on the y, negative 3 on the x. Okay, we have just a slope of 1 scenario going on, and you should see this particular line. Okay, but just also commenting on the fact that we have represented the idea that 3 cannot be in the domain. So at 3 on the positive x, we should actually have this hole that exists in the graph. And that hole happens to be something that we also sort of talked about in pre-calculus, okay, and recognizing that. Now, you can't see that on your graphing calculator screen right now. We just happen to sort of already know that concept, okay, and understand that piece of it. And I am certainly adding a little bit. If you forgot how to do that, that's fine. Okay, but that whole piece. So now we're back to this same question about limits. Okay, and according to my graph, the idea of a limit, okay, informally, is that I'm approaching a certain y value. And what is that y value? This is sort of the question that we're being asked. What's the limit as x approaches 3? So as we approach 3, okay, are we approaching the same y value? Okay, and the answer here is yes. Even though there's a hole in the graph, we are actually approaching the same y value on both sides. Okay, and that particular y value at this point, okay, might not be something that we would know. Maybe we don't know what this equation is. We could bring up our table feature and our graphing calculator and look in the table feature and see what that approaches. I will tell you right now that it approaches the value of 6. Okay, and so the limit here is going to be equal to 6. Okay, and I can tell that from my graph. I can bring up some table features. I can do some work there. Even though the hole is there, this is the idea of a limit. A limit is the concept of what are we approaching. Whether there's a hole in the graph or not, what are we approaching? Now on the flip side, algebraically, we could have done this problem without looking at the graph. So let's take a quick reminder of the algebra behind that. If you recognize this at first, that's awesome and held on to my conversation. But let's look at this particular function one more time. Okay, if we take this function and recognize the fact that the top can be factored to x plus 3 and x minus 3, then we have this cancellation of one of the factors. And you may remember that conversation from pre-calc, which is why we knew, or I knew at least, okay, that there was a hole in the graph at the value of 3. Because we have what is called that removable discontinuity. When I factor things out, I removed that idea of having a 0 on the bottom that is undefined. This then, in fact, gives us a simplified function of just x plus 3. So now if I return a little bit to my limit idea and say, awesome, the limit as x approaches 3 of x plus 3, which is the new simplified version of that, then I could do what we did before in our last example and just go ahead and plug 3 in, and I'm going to get that same answer of 6 that I got from the graphical concept. So both routes to get that limit are great options for us when we have those equations, and when we plug in that original x number, like x approaching 3, if that plugging in gives us some issues with the function, we can work on some simplification ideas, and we're going to have some of those also. Okay, so this concept of the limit and approaching things graphically, or a limit by plugging a number into an equation, those are sort of the two options that we're going to be focusing on. All right, then next, okay, just kind of also spinning a little bit, okay, understanding that part, I have in my pictures talked a little bit about these limits coming from both sides. And in pre-calculus, we also talked about the left and right approach. Okay, and I just want to make sure that we have that notation down, that we remember that from pre-calc. A one-sided limit, if I'm coming from the left, meant that I was approaching some a value on the x. And remember, we use sort of this little negative symbol as kind of almost looks like a power. And we would say things like x approaching a from the negative side, also from the left side. So we use sort of that notation to recognize that it was a one-sided piece. On the right side, of course, we did a similar thing, and we said the limit of f of x as x approaches some a from the positive side, also known then as the right side. So these one-sided limits, they do exist where we can certainly approach things from different ways. And just to kind of tie in a little bit of an example from pre-calculus on doing these one-sided limits, is we did some function work there where we had kind of those nice rational functions that gave us some branches. And in pre-calc, we talked about those branches that sometimes when we had like a limit up here as x approached 0 from the positive side, and in pre-calculus, we would say that would go to infinity. But over here, when we had a limit as x approached 0 from the negative side of the function, we said that equaled a negative infinity because it was going down. So we had different kinds of limits approaching from different sides, and that was something we discussed in pre-calc. We also just discussed the idea of a limit approaching a number. So here's where we have to make sure that we're very clear about limit notation, because we've got left, we've got right. The last two examples that I did didn't have an indication of left or right, and I talked about both ways. So now we're going to get to something very specific as kind of our last critical part of today. When you are talking about the limit as x approaches an a, that has to be understood to mean that both right and left approaches go to the same number. We call this the ordinary limit. And if an ordinary limit actually gives you a value like this L, then it is assumed that both the right and the left approach that same number. If they do not approach the same value on the left and the right, then the ordinary limit does not exist. And I'm going to show you that in some visual pictures here in a second, but I'm going to say that one more time. If the left and the right approaches do not go to the same number, then the ordinary limit does not exist. Okay, so it has to have both right and left approaches. Now, I didn't say that there couldn't be a hole there versus it being continuous. That's a different story. That's for tomorrow, by the way. A little foreshadowing. Okay, I am just talking about the limit as we approach a number. So I want to make sure as the last thing for today that I have every student understand what this means. So before I move to my next page, I'm going to warn you that you are going to, and taking notes at home especially, this is going to be challenging because I have a picture of a piecewise function that's going to have a lot of different parts to it, and I have several limits. Okay, so I'm going to change my screen now to that screen, okay, and I know it's going to be a little bit tough to copy all of that stuff probably pretty accurately, okay, and then to write all of these limits down, and I actually even have 2 more limits below this list. So if you are in fact taking notes directly from here, I'm going to give you just a quick minute to draw that picture up and to write down all these limits before I start explaining what's going on. So I'm going to pause here for just a second. If you have any questions right now about this particular graph, I'll point out a couple things. If you are making a sketch of that, okay, we have some holes that are in this piecewise function at the end. So there's a hole here, there's a hole here, a hole here, and a hole here, just to make sure you're clear. And then you have closed dots here, closed dot, and closed dot. Just to make sure in case this is not crystal clear at home. Okay, so which ones are open and which ones are closed. I'm going to erase that. And then it's also just a little bit tough possibly on the screen, okay, especially if the video is not crystal clear. So I'm going to make sure and talk through some of these limits, because if you can't see, there's some positives and negative pieces because we're approaching left and rights on there. And they're really kind of pretty light, okay, on the screen. So I will make sure and indicate that if you're taking some notes. Okay, so let's just dive into a few things here. And okay, just as a heads up, I'm going to go down as we look at the zeros together, and I'm going to go down as we look at the +1 spots together, then the 2s, the 3, and then I'm going to scroll the screen down for a couple of things on the bottom. So this first limit, it says the limit as x approaches 0, and then there's a positive sign there, so we're talking about the right. So as I look at my piecewise function, this is definitely a little bit more than what we would have done in pre-calc, but these problems are actually not that hard, and there's no work to be shown, so that's awesome. So when we think about as x approaches 0 from the positive side, and I'm going to draw each time, and then I'm going to erase what I drew for the next problem. Okay, but our approach to 0 from the positive direction means that I am coming down with my function towards a value of 0 on the y's. So this limit is 0. As I approach from the right, I approach a y value of 0. Okay, now when I look at the next limit right below that, as x approaches 0 from the left side, or the negative side, I look to what's to the left of the 0, and we have a problem here because there is no function on that side. There isn't any type of approach whatsoever. So this is a scenario where the limit does not exist because there isn't any function on the left side. There is no approach from the left. And so to help shortcut, we can go ahead and say D and E for does not exist. That limit does not exist. So the right side approach goes to 0, the left side approach does not exist. So now I'm asking a third question, the limit as x approaches 0. This is what we're referring to in the last screen as the ordinary limit. And the ordinary limit has to exist if the right and left approaches are the same. Since the right is 0 and the left does not exist, then the ordinary limit also does not exist. It does not have the same approach from positive and negative sides. All right, let's jump to the 1. Okay, and right below this, I have limit as we approach 1 from the right side or from the positive side. So here's my 1. And as we approach from the right side, the function goes toward y value of a +1. So this limit is +1 because I'm writing down the y values. As I approach 1 from the negative side or the left side, I also am approaching that same value of 1. And even though there's a hole there, my next question at the top of the next column here is, what is the ordinary limit of 1? So the question would be, am I approaching from the left and the right to the same y value? And we definitely are, because both of those answers were 1, and so that ordinary limit does exist, and it's also 1, even with the hole present. All right, we're doing well so far. Let's skip over to the 2. And 2 from the right is our next request. So 2 from the right side, we approach the value of 1. The next limit is, what is x approaching 2 from the left or the negative side? And that ends up being way up here. So as we look at this x value of 2, this side approaches a value of 4. And we see sort of that nice piecewise jump that exists there. That jump definitely means that if I talk about the ordinary limit as x approaches 2 here, we cannot say that it exists because we are approaching different y values. So there is another one of those, does not exist. All right, and our last one before I tackle, there's a couple below that, remember, and then we're almost done. So you guys are hanging on this video very nicely. So the last request that we have is the limit as x approaches 3 from the negative side. And this one was just tossing that one on. Here's my 3 value of x, and as I approach from the negative or the left side, I am approaching that value of 1. So just a nice little straightforward ending of those few parts there. The right side of that would not exist, and the ordinary limit of 3 would not exist, similar to the ones that we did with 0. Okay, I'm just going to scroll down just a little bit here on the screen because we have a couple below that here. Okay, and hopefully I don't think I totally need, okay, the actual top of the graph. So I just have these bottom 2. Notice how I've asked in these last 2 questions about the derivative. What is the limit of the derivative of f as x approaches 2.5, and then I also put as x approaches 1.5. So when you are asked to determine a limit of a derivative, which is absolutely okay, you just need to think about the slopes. Okay, and what about the slope as I approach 2.5 from the right, if I approach 2.5 from the left? Okay, are those slopes matching? So when I look here at my graph and I take a quick peek, and maybe I'll just scroll back just in here so we have that. Here is 2.5 roughly, okay, on our x value. So when we think about what is the limit of the derivative, okay, certainly the derivative as we approach from the left would be 0 because the slope is 0. As we approach from the right, the slope is also 0. So we can get a value here for this limit of 0. Because the slope is 0. When we look at 1.5, which is right here, then again we're approaching this concept here and here, and how are we looking with the derivative of that line? Since that particular segment piece is in fact a line, we would need to identify the slope of that line. And we're just going to do that quick, easy mental idea of slope. I've got this point right here at 1, 1. I've got this point right here at 2, 4. So we have a rise of 3 and a run of 1. So that slope of that segment would be 3. So the limit of f prime of x as x approaches 1.5 is also going to be 3. So I can put in some function requests. I can also have some limits with derivative requests. Okay, so these are a lot of the problems that we're going to have you guys do, mainly looking at this type of concept. What are limits of a bunch of piecewise graphs that have a lot of parts to it? Be careful to watch for those left side, right sides, and then can you declare that ordinary limit to be true because they approach the same thing? We would also, even though this example does not show it, there can be the potential for you to have some approaching infinities and negative infinities. So not to be tossing stuff all over the place, but remember a screen before, we had this talk right here about limits as we approach things could go up to infinity or down to negative infinity. And that can absolutely still be a part of your conversations in some of the piecewise graphs. So be prepared to see some of those answers also, even though the example that I did on this last screen here did not have any infinities. And we assume that you would understand that there are possibilities there. Okay, this is the first half of 2.3. The assignment that goes with it is here on page 110. This will also be typed into Canvas, so you can certainly look in Canvas for these particular problems also. And keep in mind that there's the potential for a couple of these problems to actually relate a little bit to tomorrow's chat. So do what you can today, and then tomorrow we will have the second half of the video, which mainly is going to focus on the idea of continuous. Is a function continuous, yes or no, and how do we know that part of it? Thanks, guys. Have a great day today.